Good morning and good evening. Thanks, Joe, for the introduction. Thanks to Joe's efforts that this has been a great series. I understand that the series is about Industry 4.0. The focus is on the goodies, the new goodies on AI, machine learning, big data, and so on. But what I'll talk about today is something rather new. Still, though, I believe this is something new or can be renewed in such as older subject, namely PID control. And I'd argue that PID is actually quite intelligent. And so I'm tossing out this topic. It's short, but I sort of augmented a bit. So the first part of this title, least computation, is quite clear. PID is such a device of low complexity and requiring essentially non-computation. The second part, where this has some kind of intelligence. Well, let me say the beauty lies in the beholder. The beauty lies in the eyes of a beholder. So you'd have to decide yourself. And this is, we actually have worked on this for several years now, for 3-4 years. So this work is based essentially on the joint works with my students and postdocs and visitors, Denmark, Chen, and Mao Qi, and Yong Xu. So speaking of PID, it immediately came to our mind that we have this feedback configuration where you have this physical process P you want to control, and what you do is you design a controller of this very specific, simple structure, the PID controller, consisting of 3 components, yeah? Excuse me. The proportional control, integral control, and derivative control, all right? This has been around for like 150 years. And in retrospect, even back in the days of James Watt, it has now been discovered that the proportional control was already in place in Watt's steam governor, and certainly without his awareness. And the PD control, proportional and derivative control combined, was implemented around the year of 1868 by a guy called Robert Whitehead in the control of torpedoes, yeah, weaponry, which he called a secret. And subsequently, it was around 1922, Minosky formalized this complete structure, which is exactly the form we are seeing today, okay? So many of you probably have never seen a real PID controller. Well, on the right, you see a PID control device used in pneumatic control. So you see those holes connected to this controller. And you have 3 knobs on this device and inscribed from right to left, PID, yeah? When you tune the controller, you simply turn the knobs. You have 3 knobs here. What is interesting here to see is that these knobs, each of these knobs doesn't have a full range. So you can see that the range you can actually turn this knob. which means what? Actually, when you write up the equation of Rawls-Hurwitz criterion, you will see that your parameters, the three coefficients, would be restricted to a certain range. It cannot be full range. So these knobs were designed that so that you can only turn then within those ranges. Yeah. So it's kind of amazing that after 150 years, with so many new techniques and the methods developed, the PID control remains very strong. And in the last 5 years or so, the IFAC conducted 2 surveys to polling many on the industrial leaders, industrial experts, and to find out what kind of control technology has a higher impact. The question is quite simple and blunt. Of all the techniques, technologies, control techniques, which has the highest impact? So the answer is quite overwhelming and very clear that PID. So as you can see that in 2015, this acceptance of PID control is 100% universal. And in 2018, as you can see that the question also includes the prediction of a future impact, where you see that the MPC model predictive control started to gain some momentum, but still PID control would remain to be a primary technique and device to be used in real-world industrial implementation. And that has a good reason. PID control has, over its course of 150 years, been known to be, and clearly you can see from the structure, very simple and very easy to implement, and it's cost-effective. And it goes without saying that even in these days, it's still the most popular and most widely used control methods in process industry. And having said that, we should be aware that when applying PID, we are mostly talking about low order systems, like the first and second order systems, first and second order models of industrial systems. And partly because industrial processes are oftentimes modeled by such a simple low order systems, and sometimes with a delay component added to it. And partly because PID control with really just 3 parameters for design and tuning certainly has its own limitation. So you can come up with high order examples easily, almost trivially, to show that PID control will fail. Okay, so the understanding here that I would reckon that you have this scenario that you may have a high order dynamical system, and perhaps even with sophisticated dynamics. What you do is that you simplify your model to a lower order system, let's say second order, and you treat the other residual dynamics as uncertainties. So the PID control has implicitly a very good capability to cope with uncertainty. And in my reckoning, I think this is the primary reason why it has performed so well. With so much done and know, what can be new and what further can be said about PID control? Well, even as a beginner, we have been often told that PID control is good, it works, yeah. But why? And why is it good? And how good it is? If it is good, there has to be a reason, right? As I'm quoting this word from Chairman Mao. Yeah. So let me just say a few words in Chinese. 这是毛主席在这个延安文艺座谈会议上的讲话，对吧？世界上没有无缘无故的爱，也没有无缘无故的恨。那么 PID 好，它也必须要有一个，它也不会是无缘无故的。So there got to be a reason, for these widely acclaimed attributes of PID control, and this is exactly the motivation why we re-examined the PID. We wanted to know, we want to understand a bit why it is good, yeah, and how good can it be, and certainly to the degree that it can be good, namely the fundamental limits, yeah, of the PID control in terms of its performance. And so in the recent years, we heard a lot about this term, explainable PID, explainable AI. And so in a way, what we are doing here is provide a version of explainable PID, yeah? So unlike what has been done in the past on PID, namely essentially empirical results and ad hoc rules, trial and error, design and tuning, we want to dig a little deeper to perform some analytical studies. And we use robustness of a feedback system as a benchmark, as a pilot problem, which we understand robustness is arguably the most important attribute of a feedback control system. Of all the the classical and contemporary robustness measures, and perhaps the best known are the so-called gain and phase margin. Yeah, there's also the notion of delay margin. What we are seeing here, actually, the maximum possible of these margins, gain and phase and delay margin, the maximum of these notions, these measures attainable by feedback. Okay, so clearly they have a different focus, whether it's on the variation of the gain of a system or the phase or the delay. Okay, the essential message is all clear. Yeah, despite of variation in the parameter of your interest, we wanted to know what could be the largest range of that variation, so that the system can still be stabilized by a feedback controller. And so in the classical and the present setting, we focus on LTI controllers. And you can certainly generalize this notion, for example, to adaptive control using whatever sophisticated means of feedback. Okay. There are certainly other notions like jitter margin and so on, which I'll mention at the later points. Okay. So I'll begin with first the gain and phase margin. So well, Gain phase margin are the concepts that we became familiar with in the first course of the fundamentals of control theory, right? So when you want to maximize these margins, you can actually do it analytically by solving a very simple and standard H infinity optimal control problems. Okay, the problem is posed at the bottom of this page. Yeah, and that gives you an analytical solution of the gain and the maximal gain and the maximal phase margin. And with this T, I forgot to give the what this T is. It's just the system's complementary sensitivity function. So what about PID control there? Well, the problem formulation is exactly the same, yeah, but only with this general LTI controller K to be replaced by this controller of a specific structure and complexity. Okay, so this is a fixed structure feedback controller, yeah, and we know that whenever you have something that that's fixed in structure, you are constrained in the degree of design freedom. So this problem actually is harder than where you use the general LTI controller. It becomes a non-parametric optimization problem to be optimized over these three coefficients, yeah, Kp, Ki, Kd. And as opposed to the H infinity optimal control problem, which is a non-parametric optimization problem. So we, for good reason, we consider low order physical plans, specifically first and second order plans. For the first order plans, the solutions are quite simple and clean. So we can so you can consider two cases. On the left, you have the minimum phase plan. On the right, you have the non-minimum phase plan. So for the minimum phase plan, you see that the gain margin is infinity, and phase margin is 180 degree pi, and this is the maximum you can achieve using any kind of controller. So what can we say here? For first order minimum phase plan, PID controller, actually, we're just talking about proportional and PI controller. It's as good as any controller, okay? And for non-minimum phase plan, you see that it now depends on really the ratio of the two, namely the distribution of the open loop unstable pole and open loop nominal phase 0. And one thing you can see is that the margins, whether it's gain or phase margin, are the same for proportional and PI controllers, which implies that the integral control has no effect in terms of enlarging the gain and the phase margin. Okay, yeah, and this would be a consistent observation that we will make throughout this entire presentation. And now, clearly, we want to know how good you can get to be when compared to the general LTI controller, namely you use all the means available to you, yeah, just at all costs. Well, at the bottom left, you have this gain the phase margins achievable by LTI controllers, okay? Just discarding all the other considerations, but just sheer focusing on the gain the phase margin, this is the best you can do, yeah? Now, if you compare these margins with those achievable by the proportional and the PI controllers, you just see, and in particular, if you make this comparison based on this logarithmic scale, you see that the PI controller or the proportional controller is halfly as good as the general LTI controllers. Yeah, as you can see, the gain margin and phase margin, the maximal achievable, were both half of those achievable by LTI controllers. So that's well, because we're talking about first order plans. For a lot of plans, for first order, these are already good enough, right? And typically, as we know, that you don't need that large a gain margin, and you don't need that large a phase margin. For example, phase margin when it gets to 60 degrees, it's good enough. Yeah. And that explains a bit, well, at least for first order plans, the PID controllers are good, and explains why it is good. And certainly in the extreme scenario, for example, when your nominal phase is 0 and unstable pole approaching each other, yeah, and this margin becomes 1, yeah. Which means that no matter what kind of controller you use, general LTI, the gain margin would be 0, yeah. And what about the phase margin? It would be 0 as well, right? So that actually is quite consistent with our insight that whenever you have close by nearly unstable pole 0 cancellation, the system becomes really uncontrollable. So what about PID controller, the 4 PID controller? Well, the underlying question here is that, as you can see, that if you use PI controller, it's only you can only get half of the maximum possible, right? So you clearly want to ask the question, what about I use the 4 PID controller? Notice that this plant is of relative degree 0, so you cannot really implement a PID controller, namely the derivative control, right? That would lead you to a improper system, improper plan, which doesn't satisfy the causality that is required of any physical system. What you can do is that you can use a filtered version of the PID controller, namely design the PID controller and then also design appropriately a low-pass filter. This is actually the standard practice in the physical implementation of PID controllers, simply because of the difficulty of implementing derivative control. Now, with that, you can see you can recover fully the maximal gain and phase margin to become exactly the same with this added degree of designing the low-pass filter. All right. Okay. So what I'm saying, for first order plans, whether you have minimum phase or nominal phase assistance, PID control is as good as any controllers, or at least LTI controllers. Okay. So you certainly want to go further to see whether this kind of statement, very strong statement, would work for second order systems. So we consider this. This is this is a second order system with 2 unstable poles, P1, P2, and a nominal phase 0, Z, which really the most troublesome second order system that you can expect, right? And having said that, I should add that if you have this this kind of a second order plant with a minimum phase 0, yeah, namely this S minus Z is replaced by S plus Z, yeah. Still, you can show that the maximal gain and the phase margins achieved by PID would be respectively infinity and pi. Namely, for second order system, you can second order nominal phase plants, you can make the same statement. You can draw the same conclusion that PID control is as good as any other LTI controller. Okay, so and that's why we concentrate on the second order nominal phase plant. Well, the problem becomes harder, actually considerably harder, but you can still do something, well, the same or similar. For example, you could have these analytic expressions for the gain margin, yeah, both PI and proportional and this PD and PID controllers, yeah. And you can also show that the phase, well, the result for the phase margin is actually more complicated. You don't get, at least we didn't get a equally clean analytical solution. We do have an analytical solution, but it just looks complicated. But anyway, you can still prove that whether you have PID or you have PD controller, the phase margins are the same. All right. And furthermore, you can show that in this case, the maximal attainable gain in the phase margin, yeah, by general LTI controllers, yeah, are good only within twice those achievable by the PID controllers. Okay, so that still gives us some indication, some confidence, and why whether PID is good, and explains why it is good. All right. Okay, so let me recap a bit then. The other thing I should mention is that for second order plans, you can also see that the integral control here, whether you use PI or PID, plays no role, yeah, in giving you these goodies. So, so the reason is that, as we know quite well, integral control is typically introduced. This has nothing to do with PID control alone. This just for general control purpose, you need to introduce an integral control in order to track a set point reference signal, right? So this is essentially a performance consideration. Now we have the heuristics, yeah, the insight that the performance is always seen as a trade-off with the system's capability for stabilization. Yeah, so, and that explains why integral control doesn't give us anything extra in terms of getting those margins. And actually, you can show, and which certainly philosophically makes sense, that integral control reduce those margins. Okay. What about proportional control then? It doesn't contribute anything in terms of a phase lag or lead. It's static, right? Memoryless. So it has little effect on the margins. Okay. So in all these cases, as you can see, the PD controllers always outperforms the proportional controls. So that tells us the derivative control really plays the main role here. It has the effect of improving gain and the phase margins. And the essential reason is that so those whenever you have this kind of nominal phase plans, and I mentioned that, I already stated that if you have minimum phase plans, you can get the maximum possible, right? So only with nominal phase plans, so the gain and the phase margin will be constrained to a certain upper bound, yeah. So for nominal phase plan, they always display this phase lag, yeah, and derivative control gives you a phase lead, and therefore it compensates the negative impact imposed by the nominal phase zeros. Okay, let me switch gear a bit to come down to the delay margin. Mathematically, this is a more interesting problem, and though sometimes they even appear simpler than the phase margin problem, contrary to what we believe. So this problem is a similar. All we care about is that if you have delay plans, yeah, with a unknown or uncertain delay tail here, yeah, whether you pose it in transfer as a transfer function or in state space form, you want to ask what is the largest range for this unknown or uncertain tail that your feedback controller can tolerate. That is, you want to find a single feedback controller, let's say LTI controller, to stabilize this entire family of the plans with a varying unknown delay parameter tail. So in comparison to the gain and the phase margin problems, we now have a delay component, namely with a varying factor e to negative tau s. And that makes the problem considerably harder conceptually, because now we end up with a, infinite dimensional system. So it should be mentioned for all these notions, whether it's gain and the phase and delay margin, if you do have a stable plan, those margins always infinity, or in the case of a phase margins 180 degree. So the problems are essentially meaningful for unstable systems, yeah, because we talk about stabilization. If you do have a stable plan by itself, you don't need to do anything, right? So this the delay margin problem in general is quite difficult. Conceptually, is fundamentally more difficult simply because we are dealing with a infinite dimensional system, and after all these years, it remains to be an open problem. Yeah, it's listed, classified as an unsolved problem in the edited volume of Mathematical System Control Theory, edited by Winsong, Blondel, and Makretzky. So we know in general that we cannot solve the problem with a general LTI controller. What about PID controller? Okay, so presumably you'd think that this could be even more difficult, right? Yeah, because with much higher degree of design freedom, you cannot solve the problem, and now you have a restricted degree of freedom. Do you expect to do better? Well, we have a very pleasant surprise, and we actually can solve this problem. Yeah. So this is a tau bar PID. This is the delay margin that we define. Yeah. So basically, you want to find a controller, PID controller, to make this tolerable range for the delay parameter tau as large as possible. Well, for first order plan, delay plans, still, likewise, you get a very simple, clean solutions, okay, whether for this plan without nominal phase 0 or this one with a nominal phase 0. And one thing we come to note immediately is that whether you use PID or PD or the journal, this tau bar represents the journal, the delay margin achievable by any arbitrary LTI controller, they're all the same. Yeah. So again, you can make the two statements. First of all, the integral control contributes nothing in terms of maximizing this delay margin. And secondly, for first order plans, delay plans, PID control is as good as any LTI controller, okay? Well, that actually takes us to second order delay plans. Yeah. So what we know here is that in general, to determine the delay margin is quite difficult problem. Yeah. And what you can do is that, well, you can use brute force search. Yeah. But the brute force search doesn't give you the certificate that you actually get to the maximum. Yeah. You can always come up with some solution, but you don't know whether that's local or global solution. You don't have the, namely, you don't have this certificates. So as I mentioned, no exact result available for when you use general LTI controllers because the problems are still open. So quite naturally, we wanted to know with PID controller, is it possible to solve this problem, namely to find the exact delay margin? And what is more important, can we draw the kind of insights, conclusions, like we did for first order plans? Well, it turns out this is for second order system, for second order plans, the problem is considerably more difficult. And the difficulty arises from two reasons. And first of all, you need to optimize a causal function like this, yeah, subject to a set of quite sophisticated constraints. And this function is highly nonlinear, yeah. Now the constraints consist of those conditions to ensure that the system would be stable, the closed loop system will be stable in the delay-free case. Namely, you have a bunch of inequalities resulting from the first column of Ross-Hewes criterion. Okay, and furthermore, and this is what kills us. This constraint consists of an algebraic equation, yeah, which boils down to solving the crossover frequency that we necessarily have to use in this objective function, the function we want to optimize, maximize. So now, whenever you have this kind of algebraic constraint, the polynomial equation constraint, because it has multiple solutions. So this as a whole will give you highly nonlinear and non-smooth optimization problem. Okay, so that's what makes the problem difficult analytically. And as you can see, that this is kind of nonlinear optimization or nonlinear programming problem that you'd end up with. Yeah, the inequality constraints here, and also the algebraic polynomial equation. Yeah, constraints. So so you can apply nonlinear programming results to tackle this kind of problem. And traditionally, whenever you apply nonlinear programming, it's really meant to be numerical computation. Yeah. So what departs here is that we actually try to use this, the nonlinear programming results in an analytical manner. So this is sort of requires a little leap of faith, yeah, for that purpose. And so we use sort of like the first order necessary condition for for optimality to really pin down the PID coefficients to see what kind of coefficients, what kind of range of those coefficients they must lie. And it turns out the integral control, the proportional coefficients, and here Kp star, and the integral control coefficients must be on the boundary of their allowable ranges. As you can see, the wait. Yeah. So as you can see, these are exactly the boundary of their respective range. All right. So with that, the problem reduced. So you have two coefficients already constrained, fixed. So you are left with only one constraint, that is the derivative control coefficient. Someone's reminding me. You close to conclude. Yeah, I only have a few, I think 3-4 pages. But anyway, let me quickly, let me pick up a bit pace. Thanks for the reminder, Joe. So, in that sense, we are down to a maximization problem in one parameter. So if you do brute force search, you need to deal with 3 parameters. Now we show that you need to deal with only one parameter, the derivative control coefficient. And what is even better is that this function you want to maximize in one parameter is actually a pseudo-concave function, which means that you have a unique maximum, yeah, and it's differentiable, yeah. So then these two aspects give you the tool to solve the problem numerically. You just need to perform a one-dimensional search, whether you use convex optimization, you use gradient search, whatever. Yeah, it gives you the answer. All right. So this is the so-called the unimodal problem. And what is even better is that this unimodal problem comes with an objective function that is differentiable. All right, let's start. Okay, so I think I pretty much said this essentially, so I'll skip this. So, well, no. So these are the interpretations. Okay. So quickly, let me run through this. So the for second order systems with a delay, we have seen that the PID controllers and the PD controllers would achieve exactly the same delay margin, namely the integral control, just like what we have seen previously, has no effect in terms of maximizing the delay margin. The proportional control gain, Kp, is located at the boundary of its allowable range. So which means that proportional control doesn't have much effect either, although it's necessary. Now, So I have said this about the reduction of the search from brute force search in 3 parameters to the search of 1 parameter as a unimodal problem. Now, one thing that is worth noting is that since the exact delay margin requires solving a unimodal problem, the extremement, the maximum, generally lies in the interior of the range of that variation range of that 1 coefficient, KD. So unlike in the case of first order plans, it's generally not possible anymore to get an analytical solution. Yeah. So namely, this one-dimensional convex search is as good as you can get to. You can interpret these results more broadly. For example, if you plot out the frequency responses of the PID controller, on the top you see the gain plot, and below you see the phase plot, and you immediately see that this looks like a notch filter. Yeah. So if you have some like the uncertainty in the middle frequency range, when middle frequency range is the most important range for design, right? Then this actually PID controller compensates very well the plans, and so this is perhaps why in mechanical control, in precision motion control systems, oftentimes you see PID controllers for suppressing vibrations and so on, because there you'd have the slightly damped modes, you have the modes and high magnitude peak, right? And you can also interpret this, for example, from the body gain phase relationship. You can see that the loop gain is actually quite what we want to see here. Yeah, in the low frequency range, and in the high frequency range, there's a very desirable phase leads. Yeah, and that explains why using the gain phase relationship, this PID control would perform well. However, you also see that its magnitude plot displays a quick increase of the gain in the high frequency range, which implies that if you do have unmodeled dynamics, the PID controller won't perform well. It actually will be bad. Yeah. So why doesn't that manifest itself in all the results I have presented? Because we are dealing with parametric uncertainties, whether it's again phase or delay parameter. Okay, if you do have, for example, an unstructured uncertainty, namely the unmodeled dynamics, it won't be good. And furthermore, you can sort of interpret, for example, the integral and derivative controls as sort of like push and pull amplifiers. Yeah, integral control means you have a low pass filter, and derivative control means that you have the high pass. Yeah. Filter, and so they sort of balance each other very well. And more generally, and this is some philosophical arguments, which is certainly subject to your interpretation and also your argument. So when you have the integral control, you accumulate it, you gain all the past observations. And what are the past observations? These are the knowledge, the training that you gain, right? Training. We have heard this words, in any single given day, we probably heard it, 10 times. And the proportional control really gives you the instantaneous, the present measurements. It's memoryless, right? So this I paraphrase that as an instinct of the controller, and the druid control has the predicting capability. What is the predicting capability? That's the insight and the wisdom. So you give someone the knowledge training and with a very smart, intelligent instincts, and also the insight into the future, uh, then that's very intelligent. That's intelligent control. Yeah, that's actually it's a control with wisdom, because it mimics the thinking of wise people. So so I'll skip about the extensions. So we actually a lot has been done by, for example, Qi Mao and Chen, my students. So what you are seeing here is just a small portion of the results, and quite a lot has been done by Denmark on multi-agent systems. And I mentioned about jitter margin, yeah, which really concerns the random delays in sample data system. So they were like back in the early 1990s, there were people working on the variations, simultaneous variation of gain and phase. So they call gain and phase margin. And just late last year, I saw an article published in Attribute Control System magazine by my good old friend, the late Professor Andy Packard, where they introduce this notion called the disk margin, but that's still a non-parametric measure of the uncertainty, where they try to just combine the variations in gain and the phase into one. Okay, so so I wanted to mention that in all these works, the problems actually appear much harder. That the problems are actually much harder than they appear, and there's a really beautiful mathematical theory behind it, drawing upon algebraic geometry, because you deal with, and there's also backbone using the nonlinear programming as a tool. Okay, so in this same issue of the Attribute Control System magazine, I saw in the back cover a lyric on PID by this guy, Daniel Abramovich. Is actually he claims he wrote this lyric in 2012, and this is adapted from a famous song by Paul Simon. So a lot of people, especially young people, know this name, Paul Simon. He wrote the brilliant, famous Sound of Silence, perhaps the most popular song of all time, one of the most popular songs of all time. So let me, this other ones called the Coda Quon. So let me just, maybe I play a bit. I'm not sure you can actually hear it. So what is this song about? Well, it's about this film, Coda film, right? It's a good thing because it transforms a bleak, black and white reality into a very colorful world, enriches our life. So I think in a certain way, PID control is similar. It turns a word of no control into a word where control is everywhere, yeah, omnipresent. But as we know quite well now, code of film is gone because as the new digital technology comes into our life, yeah. And now, since I'm making an analogy uh, of the PID control here, are we going to see the same with the advent of all this artificial intelligence, machine learnings, all the fancy stuff? Yeah, is would the PID control end up in same kind of fate? Namely, it will be gone from our work, our life. Uh, well, I would say no, but only time can tell. So, well, that concludes my talk.